Welcome to this lecture series in linear algebra. Last time we discussed the notion of a linear map, and let us recall some things that we did last time. So, a map from a vector space V to a vector space W, where V and W are over the same base field, let's call it F. So, such a thing is called a linear map if two properties are satisfied. The first being T respects addition, meaning this for all vectors V1 and V2 in the domain space, and T respects scaling for all scalars, alpha and V in the alpha in the scalar field and V in the vector space, basically the domain of T. So a vector space has two structures, an addition structure and a scaling structure, and a linear map preserves or respects both of them. All right. We saw some examples as to how to construct or how to generate linear maps. So given a basis and some bunch of vectors in the, or rather, if you have a basis of V, let's say basis has size n, and you have n vectors in W, then there's an easy way to send a linear map from V to W using that data. We saw that. We discussed the notion of a linear isomorphism. So we defined a linear isomorphism as a bijective linear map whose inverse, set theoretic inverse, is also linear. So that was the definition, but we ended up showing that any bijective linear map is actually a linear isomorphism. So the set theoretic inverse of any bijective linear map is automatically a linear map. All right. So here are the problems, and let's get started with the material of this lecture. So this will be a short lecture. We'll be discussing some very basic properties of linear maps. So suppose U, V, and W are vector spaces over the same base field F, and we are given two linear maps, S and T. So S is a map from U to V, and T is a map from V to W. Then just by set theoretic reasons, we can create a composite of these two maps, which diagrammatically is suggested like this. So this arrow, meaning first we travel by S and then we travel by T. So that thing is written T composed with S. This thing is also linear. So let me check the addition property, and I will leave the scaling property as an exercise. But that's a triviality. So what we have is, we have this U1 plus U2 equals, by definition of composition, S of U1 plus U2, which by linearity of S is this, which by linearity of T is that, which by definition of composition is this. So one can easily verify that the composite is indeed linear. And a piece of notation, we do not write T small circle s, we just write TS. So that is something that we should keep in mind. We will suppress this little circle that is usually present when we are talking about compositions of arbitrary functions. All right, so composition of two composable linear maps is a linear map. Composable because not any two linear maps can be composed. The domain of the second one should match the target of the first one, otherwise one can't compose. Okay. Addition. So now suppose we have two vector spaces over the same base field F, and we are given two linear maps from the first to the second one. Then what we want to show is that then the map S plus T, which does what? Which takes, how is it defined? It takes V to SV plus TV, is also linear. Again, I'll check the addition property. All of this is trivial, but I'm doing it. So we have S plus T of V1 plus V2. V1 and V2 are two arbitrary vectors in V. This is equal to S of V1 plus V2 plus T of V1 plus V2. This is by definition of addition, which is equal to, by linearity of S, SV1 plus SV2 plus TV1 plus TV2, which is equal to SV1 plus TV1 plus SV2 plus TV2, which is S plus TV1, which is S plus TV2. So yeah, addition of two linear maps which have the same domain and target is also linear. Scaling property, very similar to the addition property, is, again, suppose we have two vector spaces v and w over the same base field f, and we have some linear map from v to w, and now let alpha be some scalar. Then the map alpha t, which we define how? We define it as a map which takes little v and sends it to alpha tv. So that's the definition of this, is also linear. And let me not do this one. It's very, very simple. I don't want to repeat the same things over and over. All right, so these are some basic constructions of linear maps out of already given linear maps. One is composition, the other is addition, the other is scaling. All right. Now look at some other properties of linear maps. So fix a linear map, where of course v and w are vector spaces over the same base field. Let us keep in mind that that symbol is f if needed for the base field. We define two concepts. One is the kernel of t. So this is called the kernel. And the definition is all those vectors which map to 0 meaning additive identity of w. So all those vectors which map to 0 under t, that is called the kernel of t. And we define the image of t. Well, this is a set theoretic concept. It's just exactly the image of t. You just take all the points of the form tv, where v varies over the domain. So that's exactly the image of t. And the fact is, kernel t is a subspace of v, and the other fact is image t is a subspace of w. So why is kernel t a subspace of v? Let me check addition. So let v1 and v2 be in the kernel. Then we want to show that their addition is also in the kernel. But this is equal to by linearity. But that by the fact that v1 and v2 are in the kernel is 0 plus 0, which is 0. So that's it. The summation, so kernel is closed under addition, and similarly one can show kernel is closed under multiplication, and that's it. Similarly, this is an exercise, image. Or maybe image is a little bit more interesting, so let me do it. So let w1 and w2 be in the image. Again, I'll only do the addition. So we want to show that w1 plus w2 is also in the image. So let v1 in v be such that, or okay, let v1 and v2 in v be such that tv1 is w1, tv2 is w2. Why? Because since w1 and w2 are in the image of t, that by definition means we can find v1 and v2 in the domain whose t image is, t image of v1 is w1 and t image of v2 is w2. We are not trying to say that you can find unique such v1 and v2, there just exist such things. But now by linearity, we have t of v1 plus v2 equals tv1 plus tv2 equals w1 plus w2. And if we look at this part, then we see that w1 plus w2 is indeed in the image of t, because there is some vector, namely v1 plus v2, whose t image is the sum of w1 and w2. So that's it. One can also check scaling, and that's how both of them are subspaces. Lastly, we have another very interesting property, is that suppose we have a linear map, and of course then these two are vector spaces over the same base field. Let's call it f. So suppose this is a linear map, and u is a subspace of w. Then this is a subspace of v. And what is this? This is a set theoretic notation. This means those vectors in the domain of t which map to u, which map inside u under t, is the pre-image of u under t. Okay, so what is the proof? Let v1 and v2 be in this pre-image. So we want to show that addition is in the pre-image, and similarly, if we pick an arbitrary vector in the pre-image, we want to show its scaling is also in the pre-image, but the scaling part I will leave as an exercise. So wanting to only show that T inverse U is closed under summation, what we have is, by definition, TV1 and TV2 are both in the subspace U, which implies since U is a subspace, their addition is also in the subspace. which implies by linearity of T that this is in the subspace U, which implies V1 plus V2 is in the preimage. So preimage is closed under addition, similarly is closed under scaling. Okay, let me just draw a diagram which I like. So we have a situation like this, and we have this. This is T inverse U. Sorry, what am I doing? This is T restricted to T inverse U. And what are these vertical maps? So this map is just U going to U, and this map is V going to V. So check that. These are also linear maps. These are called inclusion maps. I don't know if I said that in the last lecture, but I'm saying it now. So if you have a subspace of a vector space, then you have a natural inclusion, which just takes a point in the subspace to the same point. This has nothing to do with linear algebra. This is a set theoretic notion. If A is a subset of B, you can define an inclusion map from A to B, which takes little a to little a. This makes sense because, of course, little a is a member of B also. Okay, and so these are linear maps, and this original linear map kind of restricts, it actually restricts to a linear map from a subspace to another subspace. In this diagram, we say commutes. Commutes meaning if you go this way or that way, it's the same thing. So that's what commutation means. All right. So I think this is all. Yeah. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.